Okay, so we are also streaming live on YouTube now. So whenever the class is over, you'll be able to watch the replay there. So that's set up. So what I'm gonna do now is I'm gonna go ahead and come back to you in Zoom. So let me do this. All right, so I'm here with you guys now in Zoom. I can see all your questions. I can see whatever you're writing in the chat. So definitely feel free to use the chat very liberally and use your emojis to let me know if you're like, if it's this, if it's that, if you're like sad, if you're like, whatever it is, just let me know. But also feel free to unmute and talk to me. I'm gonna ask you questions throughout, and I'm gonna ask people to like draw on my screen and like be interactive, okay? So definitely, I hope that you're ready for that, that you're ready to be engaged, okay? Because that's how I approach it. I don't want anybody to be just sitting there like this and just being like, it's just another class, you know? I want you to get the most out of it, and so I want you to be and well engaged, okay? So I see Beyonce saying good evening, Beyonce, good evening and welcome. So far it's Beyonce, Kelsey, and Sham. Welcome, welcome. Thanks for being on time. We're at 5:03 now, so let's plan on beginning at 5:05. Let's give everybody else just a little bit more time to get here. And in the meantime, if you have any specific questions, anything that's specifically that you'd like to see over the next 3 weeks, please let me know. Today I plan on doing organic chemistry though, just like some fundamentals on it, and then we can build from there, or I can alter whatever it is I was planning on teaching based on what you say. So if you have anything specific that you want to see from me, you can go ahead and drop it in the chat while we're here. But let's give anyone else that's coming a few more minutes. So it's 5:03, so let's give them until 5:05, okay? All right, so that's where we're at right now. In the meantime, let me pull up my slides as I have prepared for today. Let's see here. Let's see. Okay. 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 So I'm sharing my screen right now. Can you see my screen? Give me a thumbs up if that's all clear and looking nice on your end. Just let me know, and we're giving everybody else a minute. Okay, so in a minute, we're gonna go ahead and just jump right in to all the stuff that I have prepared for you today. So let's see if we'll need more than an hour. I know for my CXC class, I think we're maybe gonna have to extend it a little bit longer than an hour. So let's see what happens with what I've prepared for today and how much you guys interact with me. So I want you guys to interact, okay? Talk to me, ask questions, give answers, do all of that stuff. This is the place for that. This is the forum for that, right? Anything that you're afraid to do in your regular school class because I don't know why, for whatever reason, don't be afraid here. So feel free to ask all your questions, okay? So it's 5:05, so I'm gonna go ahead and get started. And I'm gonna give you guys just a little bit about myself and what it is I'm doing here. So if you saw me on Instagram, maybe you saw the Instagram live that I did. I did 3 of them, just kind of detailing my background and why I'm doing these free chemistry classes and that whole stuff. So I'm Nyla Ruddock, and I was born and raised in Jamaica. I'm from St. Thomas, so that's on the eastern end of the island. And so I went to Mark Bay High School for 1st to 5th form. And then I went to Campion College in 6th form, and that's in Kingston. So I did lower 6th and upper 6th form there. And so for 6th form, I did physics, chemistry, and math because I was set on being a chemical engineer, which is what I am today. And so I did physics, chemistry, and math, upper 6th and lower 6th. And then initially I wanted to go to Trinidad, which I know I have a lot of Trinidadians here with me today. I wanted to come and move to your lovely country to go to St. Augustine, to that UA campus to do chemical engineering. But I was exposed to a variety of ideas when I went to Campion, and that kind of led to me looking into America and Canada and studying in those parts of the world. And so I applied and I got into Stanford University, which is in California. They're a very good engineering school. So that's where I went. I did chemical engineering. I got to study abroad. So I went and I lived in Germany for a bit and I did an internship there for the entire summer. So that's when I was I was a sophomore then. So I was in my second year and I got the opportunity to study abroad and I went and I came back. And then as I was thinking of focusing my career and what I might want to do with my chemical engineering degree, I was learning more and more about, just the amazing things that you can do with STEM, a degree in STEM in general, but specifically in the area of biotechnology. So I wanted to use biology and those transformations that we can make and really apply my chemical engineering degree to improve the lives of people through healthcare, so to make better medicine. So that's kind of what I spent my years after graduating doing, doing research in that area. So cancer therapeutics, precision medicine, just learning about that whole space and contributing to that space. But everything that I did in college and beyond was really driven by then a desire to come back to Jamaica and to really apply those things here and to grow, the region and the country and to make us more competitive as far as STEM goes. And that's kind of why I launched this LMD and STEM Academy. So I'm the founder and CEO of this academy here that's providing you with free CAPE and free CXC classes for the duration of February. This is just a small dent in that, or a small starting point for me. I have a lot of other things planned, but this is where I'm starting. So just so you know a little bit about me and kind of my motivations for doing this, I really want to see, the Caribbean become a thriving STEM ecosystem, a place where people can look to and be like, oh, the Caribbean, they are leaders in XYZ, right? They're leaders in biomedical innovation. They're leaders in this, they're leaders in that. And that's really what will help us to propel ourselves to the next level, I think, as Caribbean nations. And so that's kind of my spiel, like my little, rundown. So that's kind of who I am and why you're here and why I'm here. So with that, I'm gonna jump into the topic here, right? So write in the chat for me what unit you are. Are you upper six or are you lower six? Because what I have prepared for today is organic chemistry stuff. So it's chemistry of organic compound, which is an entire module to itself, right? Because it's so vast and it's so deep and it's really in everything around us. Organic chemistry is so vast and so deep that I think that even CXC students who might be joining in just out of curiosity can benefit from it, right? And even if, whether you're an upper six or lower six, you can benefit from this. But I wanted to know from you where. So drop in the chat for me. Are you in unit 1? Are you in unit 2? And where are you from? So write where you're from as well in the chat. And then I'm gonna give you the exam dates right now. Oh my gosh, if I can find my CAPE unit 1 dates. Let me see. I have CAPE unit 2 dates right here, but let me see unit 1 so I can tell you that, so you have an idea, you know what you're working towards. If it is that you don't know, that you don't yet know the dates, because maybe you don't know as yet. So I just wanted to give you that. So when you're crafting your study plans, you know what you're crafting, what your deadline is, so to speak. Okay. So right from in the chat, I haven't seen anyone. Oh, I do see now. Okay, so Sham Prasad. Sham says he's in upper six, Beyonce is in lower six, and Kelsey is in upper six. So I'm from the sweet Trinidad and Tobago, and I'm doing unit 2. Beyonce is from Jamaica, she's doing unit 1. Kelsey, where are you from? Kelsey. Okay, so I have 2 unit 2 and a unit 1. All right, Trinidad as well. Okay, welcome, Trinis, welcome. Okay, so let's I'm going to give you the dates, right? Both unit 1 and unit 2 dates. So CAPE unit 1, paper 1 is on May 17. No. Paper, which one is this? Yeah, paper 1 is on May 17 and paper 2 is May 5th. right? So this is from the CXC website. So it's just a date for you to have in mind. So by the time April ends, which is like, so we have all of February, all of March, all of April. So you essentially have 3 months to get this thing done, like get this thing together, you know, get all your questions answered, get things clear in your head so that you're not, you know, confused. All right, so I see Kelsey wants both dates. Okay, so I have unit 2 now for you. So paper 1 is on June 6th and paper 2 is May 9th. So the paper 2 comes first, and the paper 2 is really the bulk of the stuff, the meat of everything, where you have to sit down there with a pen and a paper and you are crafting your own answers based on your understanding of the content, right? It's not multiple choice. So the answer is not like the answer is going to be there. You are the answer, right? You are the answer generator. And those ones are coming in early May. So May 9th is paper 2 for unit 2, and May 5th is paper 2 for unit 1. So keep those dates in mind as you craft your study plan, if you haven't already crafted that. So you have roughly 3 months to turn it around if it's not going well, and 3 months to make it perfection if it's already going well, okay? So that's just a note for you there. All right, so now let's jump into the presentation for today. So as I said, the topic that I'm doing today, I'm starting on is organic chemistry, and that's the chemistry of carbon compounds, essentially, right? So it's carbon that's really at the core of all of these organic compounds and really at the core of organic chemistry. And so let's see here. So I have an outline of the entire module, right? That is chemistry of carbon compounds. So I have an outline of the entire module for you. And so essentially what you start out with is structure and formulae. And then you go into functional groups, reactions, and mechanisms. The reaction mechanisms is a very deep thing, a very vast thing that, you know, we're not going to get to it today, but we definitely will get to it before the month ends, right? But that's a very, very deep thing. We're going to focus on structure and formulae today. But the third one would be then acidic and basic character of organic compounds. And then the fourth one is macromolecules, so like your polymers and all these cool structures that we're able to then build from carbon, and it's all these diverse properties that it has that really enables us to like just do amazing things and amazing things in nature too, right? Naturally occurring things that are based off of organic chemistry and have a carbon basis, right? A carbon backbone, and the things that you can do with that. So as I said, this is like an overview of organic chemistry. Today though, for our 1 hour session today, we're going to focus on structure and formulae. So that's just that top one, okay? So under that, so within structures and formulae, we're going to focus on the special features of carbon. Like, what is it that make carbon so special? Like, why is carbon so special? Why isn't it something else that has this whole branch of chemistry to itself, right? That can create all these vast array and complex structures. Like, what are those special features of carbon that gives it that, you know, sort of flexibility, right? And then we're going to talk about an homologous series and that whole thing. And what is that? How does that come about? And what does that look like what does that have to do with you? Okay, essentially that. We're going to talk about empirical, molecular, and structural formulae. And we're going to talk about how we can determine formulae from experimental data. Okay. All right, so let's just jump into it. I gave you all the answers. The special features of carbon. I wanted somebody to walk me through them. But what I'm going to do is I'm going to have each of you explain to me what these different special features are. So don't let me pick on you. I'm going to let you volunteer yourself to tell me what are each of these special features. What do we mean by catenation? What do we mean by tetravalency? What do we mean by resonance? And what do we mean by hybridization? So who wants to go first? Just walk us through that, because these are very important things to the starting point. And so I want to make sure that you guys are aware of these things and why and how they then play a part into how we can then start building forward into organic chemistry. So I see that Sham is highlighted. Are you speaking to me, Sham? Do you want to take one of these and explain to me what's going on here, what these features are?
Yeah, miss, no problem. Which one? Anyone?
Anyone, just pick yours. Yeah, pick your favorite one.
Right. I think hybridization, that is the energetically favorable process where you merge the s and p orbital together to form a hybrid orbital.
Yeah, that's perfect. So they form new orbitals with 4 unpaired electron, right? And the energy intermediate between the s and p orbital. So that's great. So that's that hybridization. And Shams, how much do you know about orbitals? Are you comfortable with atomic orbitals and that whole concept?
Yeah, to a good extent, yeah. Like the p orbital is 3 could hold 6 electrons because each orbital could hold 2.
Okay, yeah, that's great. All right, so you've mastered that. That's a unit 1 topic, right? Primary, largely. That's where you started to learn about those orbitals. Yeah. Okay, so Beyonce, you're in unit 1, so you probably don't know. Well, you probably have an idea of organic chemistry from CXC, but you've probably started to learn about atomic structure and orbitals and atomic orbital theory. Is that correct, Beyonce? Like s orbital, p orbital, energy levels, and subshells. Have you started to learn about that as yet? Let me know in the chat. Okay, yes, miss, just the orbitals. Okay, great. So yeah, so what Sham was saying is that those orbitals have in particular for carbon, they can hybridize. So hybridization is kind of, the word hybrid means like a mixing, right? There's like a mixture of things that go on. So you have those orbitals mixing, and then you have 4 unpaired electrons, and then you can have these vast array of compounds that then arise. And I see that Kelsey took catenation. So she's saying that catenation is a bonding of atoms of the same element. So that's the carbon then, Kelsey. That's like a carbon bonded to a carbon bond to another one. And then you have these long complex chains, right? That then form as a result of that catenation character, that catenation ability of carbon. And then of course we have tetravalency, which is really like, I think, a cornerstone principle here. Is that what does tetravalency mean? Does anyone remember? I'll let you define that for me instead of me telling you. So what does tetravalency mean? Tetra, what does tetra mean? It's just 4 valence electrons, right?
The ability to hold 4 electrons.
What was that, Sham?
Yeah, the ability to hold 4 electrons.
Exactly. So it have 4 outermost electrons in its in that outer principal quantum shell, and so it's able to form bonds with other atoms as a result of that, right? And largely, what kind of bonds are we talking about? What kind of bonding events do carbon atoms take place in? Anybody? Like, what kind of bonds are they forming, these carbon atoms?
Covalent.
Exactly. It's largely covalent, right? And they share 2 electrons, right? Well, it depends on the bond that is being formed. It can form 4 bonds, really. But a covalent bond itself is formed by the sharing of 2 electrons. So 1 from you, 1 from me, and we're sharing. And now we're able to attain that noble gas configuration, since that is really the goal of bonding, right? The goal of bonding is so that we can become more stable and like the noble gases, right? Does everybody remember that from CXC? The reason why bonding even happens in the first place? All right, so that's tetravalency. And then now we talk about resonance. And resonance is kind of an interesting concept. And again, largely based on this idea of orbitals and molecular orbital theory, that there would be resonance structures and these kinds of things, right? And so resonance is essentially a concept that's related to let me say, like, I mean, I say a random, but like the ability then for these electrons to exist. So you can find them in different locations, right? And the way that we describe orbitals is, so it's a probability of finding an electron in that particular location. That's where an orbital is. So like for resonance, you have overlap. The molecular orbitals extend over 3 or more atoms. And so because of that, what you have is that you will have a structure. Let me see if I can draw it here. The one for benzene in particular comes to mind immediately, where you will have a structure like this. So you have like a benzene ring, right? Do you guys know this structure? Or Beyonce maybe you remembered from CXC, but essentially you're able to draw this ring structure in the middle. They call these aryl. So this is like an aryl group. And this is just what a benzene would look like. But the reason why it looks like that is because they're taking into account that you have these resonance properties where you have the electrons being able to rearrange and be found on different locations. So let me show you what that would look like without the ring, so you can kind of see when we speak about resonance what we mean. So I'm just explaining resonance to you here, just so we're all on the same page, right? So typically you will have this, you have alternating double bonds. When you look at benzene, it will look like that, right? But a resonance structure, or resonance mean that that bond could be, let me number our carbon. So we have 1, 2, 3, 4, 5, and that's our 6th one, right? So now, right now, as I've drawn that, we have the double bond between 1 and 2, double bond between 2 and 3, double bond between 1 and 2, double bond between 3 and 4, and double bond between 5 and 6, right? But the property of resonance means that that bond or those electrons can be found at a given snapshot in time. Those electrons can be found on different, that double bond can be found on a different atom, a different carbon atom, and that's because the molecular orbitals can overlap and then spread over 3 or more of these atoms, right? So where did my pointer go? Let me show you that real quick, how the bonds are gonna can shift at a given snapshot in time. So when you take a picture of the benzene ring and you just look at it, you'll see that the bond, maybe you see the bond somewhere else than before, right? Because the electrons are rearranging, and it has that property. So let me see if my thing is there. All right, so now I put the double bond there. And so they remember that they're alternating. So the other one would be here. Oh, I'm drawing lines now. I don't want to draw a line. I want to have a free form thing. So let me get the free form. Free form, not a line, not a line. Let me draw it again. Okay, so I'm like, just basically I'm showing you that the where the double bond is shifts, right? Because before it was like, well, it was like between 1 and 2. Now it's between 2 and 3. No, this other one is between 4 and 5 as opposed to 3 and 4. And then we have the other one up here, right? So we have 1, 2, 3, 4, 5, 6. So instead of it being between 5 and 6, now it's between 6 and 1. So is everybody kind of clear on that idea of resonance? Is that you have the electrons just kind of shifting positions throughout the structure. And so at the end of the day, what you have is that they're not distinct structure per se, they're a single structure. They're like in between structure. It's not even a mixture. We wouldn't refer to it as a mixture of structures. It's not. It's a single structure. But like if you take a picture and at any given snapshot in time, you'll see that the electrons are found in different places, right? Is that clear to you guys? Give me a thumbs up so I can know that it's clear to you and that you're not like just completely lost on this concept of resonance. So, okay, so I see all the thumbs up. That's great. All right, so the force, just to recap, the 4 special features of carbon that makes it so flexible, so it can have its entire section of chemistry to itself, organic chemistry, is because of catenation, which Kelsey told us is the ability then for carbon to bond to another carbon, another one, another one, another one. So you form these big old long chains, right? Long chain carbons because of catenation. Shams told us about hybridization and how you can have the s and p orbitals overlapping, and that we have these hybrids forming, this hybridization process that helps carbon to then have this diversity and a range of compounds being able to form. You have tetravalency, which is this idea then that carbon has 4 valence electrons in its outermost shell, and so it's able to bond, participate in a lot of bonding, right? You can share a lot of share those 4 electrons with different atoms and get to that being able to build a compound and a vast array of compounds. And then we have this idea of resonance, which is essentially the ability for these electrons to be found in different positions around the carbon chain. And so this is as a result of the molecular orbitals being able to extend over 3 or more atoms, okay? All right, so I'm gonna just move on from this now. And then now let us move to the next slide. Let me clear that screen first. So we're gonna speak about an homologous series now, okay? And so you see here, I'm very big on fundamentals and I'm big on building things and having things just like go in a methodical order. And so this idea of a homologous series follows nicely, Kelsey, with this idea of catenation, right? Because the way that we're able to form a homologous series, which is just a series of carbon compounds that are different from each other by only by the addition of more CH2 groups, right, to increase the chain length. So we're increasing the carbon chain length by CH2, and that results to us having a vast array of compounds. So they're in the same homologous series, right? That's defined by what the functional group is, and we'll get to that later, but you'll have, like, say, let me show you. You have a homologous series of, say, alkanes, right? So you have your alkanes, and your alkanes, you have your first one is this with just 1 carbon. So this is methane, right, guys? Methane. And then you have a C2. What's this? 2N plus 1. So what's this? What's the formula of ethane? Anybody can tell me? So it's C2 what? C2H5, right? And then C3, so it's 2N plus 1. That's a general formula of alkanes, right? So it's 3 times 2, 6 plus 1, 7. Right, guys? So you're seeing how you're adding a CH2 each time. Right? So then that tells me that this is 6. You're adding a CH2 each time, so this is 8. Right? CH2, and then you add a CH2 to that. Are you guys following that homologous series? Let me know. Feel free to unmute and let me know what you guys are thinking about this. Right? Where are we with this? Okay, so Sham is giving a thumbs up. Kelsey, where are you with this? Is this good? Okay, and Beyonce says it's good too. Okay, and let me see who's saying something in the chat. Somebody's talking in the chat. All right, so that's your homologous series, right? And you have an homologous series for each of the functional groups. You have a homologous series that you always kind of grow based on what you know about these alkanes, right? So they're kind of like, you kind of harken back to this idea that alkanes have this homologous series where you have 1 carbon, then a 2nd carbon, then a 3rd, 4th, 5th, 6th. But then the difference is that you're gonna have the functional group, and that's what's gonna dictate what the particular homologous series is of, right? So you have a homologous series of aldehydes, of ketones, of alcohols, of alkenes. So this homologous, this idea of a homologous series extends throughout organic chemistry, really. So it's important that you're aware of this, and that you're aware of, essentially, it's because of catenation that we can do this, right, Kelsey, that we can be adding these other carbon and these other carbon, this other carbon. And so we have, in the end of it, we have an homologous series of compounds, right? And so what I just showed you there was the homologous series for alkanes, but you can do that for the other functional groups as well, okay? So that's this idea then of a homologous series. Let me clear the screen and advance the slide if we're okay. Are we okay to advance? Is that all clear? Okay, great. All right, so let me clear this and move on. So we have a clean slide. Okay, so the compounds in this homologous series are named according to the IUPAC naming system. So how comfortable are we on a scale of 1 to 10 with IUPAC naming in this group? How comfortable are you guys with naming compounds? Like if I were to say, give you a name and say, somebody draw this for me, who would be able to draw a compound for me right now? Like just solely based on the IUPAC name that I give to you. Who would be able to do that right now? I'm gonna pick somebody and test you on this right now to see where your understanding is, right? How comfortable are we with this? Kelsey, Sham, Beyonce, how comfortable are we with this idea of an IUPAC naming system and being able to name these compounds? On a scale of 1 to 10, let me see. I see there's some activity in the chat. I'm gonna check on it real quick. So you guys are putting your comfort level in the chat, because I'm gonna come back and look and see. But I'm looking for something to give you, one of you guys to draw. Yeah, I'm gonna ask you to draw something to test you, but let me hear what you say about yourselves. Oh wow, we have a wide range here. All right, we have a wide range. So let's see here now. So I'm gonna, let's see. Did I have one on the other side? No. Okay, let me just test you guys really quick here. So let's see. I'm gonna give you this just to see, right? And so we can all see where you are with this. So who would volunteer to draw? Or am I gonna be stuck with drawing it if I ask you to draw it? Can I have a volunteer to draw this? So draw 3-methyl, right? So the methyl group is on the 3rd carbon. I'm giving that away, right? I'm giving whoever is volunteering to do it that little nugget. So it's 3-methyl pent 1 ene, right? So right away we know that this is an alkene, right? That's an alkene, so there are double bonds involved, right? So you know this, I'm kind of assuming that at some basal level a functional group understanding from you, but if not, I can definitely go over that. But alkene is just a double bond carbon, right? So is there a volunteer to draw this? Can I have a volunteer to just draw on my screen and just draw me how you would draw this in your mind? Like how would we proceed from here? Who is volunteering themselves? Anybody? Let's make this as interactive as possible. I don't want to be talking at you. I want you to be engaged. So who can draw this? I want to pick somebody. I'm going to pick on somebody. Kelsey, can you draw this for us? Let's see. Let me see what's going on in the chat. Okay, I see what Kelsey says. Sham, do you want to give it a shot?
Yes.
Okay, so go ahead and draw on my screen. I think you have that capability. So draw on my screen and let's see what you come up with. For 3-methyl pent 1 ene. So I gave you the nugget there. We're looking at an alkene here. Methyl pent 1 ene. So that means that there are there's going to be a straight chain or a region that has just 5 carbons, right? And on the third one, there'd be a methyl group hanging off, right? So I think that that's enough for you to be able to figure it out. Okay, I think that works, right? And all our carbons are satisfied. So just draw me something to let me know that they're all satisfied. That tetravalent, yeah. So just put those there so I know that you have H3, H3, H3. There's a H there, H there. And then on the third carbon, you have that methyl group hanging off. You have your alkene group there. There's like, I think you overfill this one, Sham. Remember that therefore you overfill this one because it's a double bond, remember? So you have to take out back one of those. Do you see it for the second carbon? Yeah. Yes. All right. So only two and then you have that. All right. Perfect. See? There you go. That wasn't too bad, was it?
No, it's
All right. All right. So let's keep it moving now. Is that clear to everyone else here? Kelsey, do you follow that? Beyonce, do you follow that? How you're like, oh, there's three. You have a region where there's five carbons in a row, and that comes from the pent. That pent is the hint, right? That five. And then one in tells us that on that first carbon, we have a double bond. And then 3 tells us that on the third carbon, we have a methyl group hanging off. Okay? So that's kind of how we're able to break that down real quick. If you need any further help with that whole idea, definitely send me a message and I'll be able to help with you. I'll try my best to help you with that IUPAC naming system. But let's move on from here now. So let me clear this. Let me clear this. Okay, so clear my drawings, and then I'm gonna come out of this annotation thing for now, and then move on and advance the slide to the next thing that we have here, which are types of formulae. All right, so now we're gonna move forward. The types of formulae. We have empirical formula, and I want you guys to just shout out what these are to me. I'm gonna populate all of them, and as I do so, you tell me what they are. What's the empirical formula? Just shout it out for me. So go ahead and unmute yourself, guys, and just like shout out what each of these are as I populate them. Okay. So tell me what's the empirical formula. And then what's the molecular formula? So just go ahead for me and just tell me what those are. So we have empirical, molecular, then we have structural, we have stereochemical, and then we have, what's that one? We have a skeletal formula, right? So the empirical is just the lowest, well, the empirical is just actually what you get from that, what they call empirical evidence, right? So you can get that from the data. If you're given data, you can derive the empirical formula from that. So it's kind of like a basic formula that you would get, and it's typically the numbers that you have is like the lowest, in the lowest form, typically for an empirical formula, right? Right, guys? Come on, man, interact with me. Interact with me today. This is a fairly small group, so just let's be interactive, right? So is that clear to you guys? Do you remember that? Or is this, or am I going too basic for you guys? If it is that this is too basic, let me know, let me know if you're snoozing off on me or whatever the case may be. Let me know why you're not speaking, or maybe you're not in a position where you can be speaking. Let me know either way, okay? Let me know what's going on there, because I want you guys to engage with me and interact with me and tell me what these, what are these formulae, these different types of formulae, because it's very important that you know what they are, so that as we move on to this idea of isomerism, that you can then you're able to navigate that with ease, right? Because you know what the respective formulas are. So let me see. Somebody saying something in the chat. There's some talk in the chat. Let me see. Yes, miss. I'm okay with this. I need a recap. Beyonce says she needs a recap. Okay, so Beyonce is the only one that said anything. Sham, Kelsey,
I
where
was
are you?
going through this molecular that deals with the actual number of atoms.
Exactly, that's right. All right, what else? Structural. What did you say about structural? What can we say? What can we say about structural?
That shows the arrangement of the molecules.
Yeah, so the actual structure, right? Like you draw an actual structure, like you just did. Like you actually just drew a structural formula for us on that previous slide, right? And then the skeletal is just the skeleton, like the bones of it. So you probably wouldn't even write, you wouldn't even write carbon. Really? Let me show you what a skeletal look like. You're assuming that the person looking at it knows that you're talking about a carbon atom. So you wouldn't even write carbon in it when you're doing a skeletal structure. When you do a skeletal structure, you just draw. Let me show you what it would look like. Let me see if I have my pencil. Oh no, I don't want a diamond. I want my free form. So let me get my free form pencil again. Shams, do you have your pencil? Can you draw it for me real quick? Let me see. I think I got mine now. Skeletal is something like that. It would be something like that, right? And you can, did you see what I just drew? 1, 2, 3, 4, 5, 6. That's a 6 carbon chain alkane, right? And then if we wanted to like we can put double bonds on it too and say, oh, that's a alkene, right? Did you see what I just did? I just drew a double bond there. So that's a skeleton. It's like a skeleton. It's like the bare bones of it. We don't even have any letters in it, right? And then we have a stereochemical one, which basically just gives us the shape, right? So we get the bond angles because there are different bonding angles of what forms when we have these organic compounds. You have tetrahedral structures, you have you have all these different angles or these different arrangements or these conformations that you can have these compounds in. And so a stereochemical formula would show you that. Okay, are we all good on this slide? Let me know so I can keep it moving. Let me know. Just give me that thumbs up so I know. Okay, I see those thumbs. All right, so we're gonna move on to the next slide, the next idea, big idea here. So I'm going foundational, guys. I'm going fundamental with you today. And as we continue to meet over this month long, then I'll add on the level of complexity, right? But what I don't want is for us to get to week 3 and you're just like, I don't know that, right? So I'm taking the time up front now to teach you the fundamentals, okay? So that's what this is. So if it's too slow for you, still let me know though. But that's the whole reason of why I'm doing doing fundamentals right now. Okay, so next slide. I think I just did this type of formula and I gave you something to draw. So now we're on to this. Let me clear this real quick. Let me take this off. Okay, there we go. Okay, all right. So we're doing this idea of structural isomerism is where we're at right now, right? So we're talking about isomers. And I didn't define isomers before anywhere on these. So does anyone know what an isomer is? What's an isomer? What does the word iso signifies? What could an isomer be? Before we even talk about structural isomer, what's an isomer? Period. Anybody can tell me that? I want you guys to talk, like I could just tell you what it is, but I want you guys to be engaged. So that's why I'm asking you to tell me what the things are, right? What's an isomer? What do you remember about isomers? Iso.
Yeah, the same molecular formula, but they're arranged differently.
Exactly. And so that's essentially what the structural isomerism idea is that you're placing the functional group in a different position on the chain, right? But the formula, the overall formula is going to be the same, but you're putting the functional group in a different position. And the functional group is essentially what gives the compound its character, right? So we would refer to the double bond in the alkene as a functional group, right? Because that confers a lot of characters to it by virtue of there being that double bond with those 4 electrons there, right? So that's just what a functional group is. If you put the functional group in a different position on the chain, then you get a strong structural isomer, right? And so under structural isomers, there's this idea of positional isomers. And so with positional isomers, that's directly the position of the functional group that you're changing. And so the physical properties may vary slightly, but not completely, because the functional group in those 2 compounds is still the same, right? It's just the position and what it's then being positioned close to that would probably determine what the physical properties then are and what the chemical properties then are, okay? So you have propan 1-ol and you have propan 2-ol, right? So that just tells you the position of the OH group. So the functional group of an alcohol is OH. So that OH would be placed in a different position. In this case, it's on the first carbon, and in propan 2-ol, it's on the second carbon. Okay, so are we clear on that? And are we seeing that difference in boiling points? Are we seeing that? Okay, great. So we're seeing that difference in boiling point that arises as a result of the only thing that's different is the location of that OH group. Okay, so that's positional isomers. And then I want somebody to volunteer to draw the positional group isomers that have that molecular formula. So this is why we went through those great lengths to describe, to define what molecular formula is, right? It's just that with the actual number of each atom that you have. So I want you to draw the positional group isomers that have that molecular formula. So that's C3H8O, okay? And so in the interest of time, I want somebody to do this real quick. So you don't have to draw, yeah, you don't have to draw everything, but just give me an idea as to what we might get from this molecular formula. Who feels comfortable doing this right now? Let me know. So we're not here waiting. Anybody wants to do it? Anybody? I want you guys to be engaged, you know. I don't want to be preaching to you. I want us to have a discussion and I want us to interact, okay? So if anybody wants to do this, well, actually it's C3H6O. Right, so that's a little typo right there. So it's C3H6O. Anybody wants to draw that? You can draw an aldehyde and a ketone. Right, from that. Anybody wants to draw it?
Monsieur, 2 joints.
What was that?
2 joints.
If I have what? I can't hear
No,
you.
if you want 2 joints.
I didn't hear what you said. I don't know why I'm not hearing you clearly.
MSC, hear me good now?
Yeah, I can hear you now, yeah.
MSC want the 2 joints.
Yeah, you can draw the 2 drawings. So this is a 6, right? So it's C3H6O, and then you can get as a functional group isomer, so you can get propanol out of that and propanone out of that. Because it's literally just the position that's there. It's a functional group isomer, right? So you're drawing, which one are you drawing now?
This is propanol.
Propanol. So I don't think we can get propanol from this. You can get propanal, which is an aldehyde, because like, look at this now. Propanol, you would have, let me see. Yeah, you're gonna have more than 6 hydrogens, right? If it was propanol. Let me be clear that I'm saying propanol.
You had the 8.
Yeah, you'd have 8, but the 8, so that would be what it would be for 8. Yes. So do you want to continue with that, or do you want to switch to the 6, C3H6? Because that's what I was meaning. I had a typo, but I was meaning to put C3H6.
Yes, I'll switch to the 6.
Okay, yeah, but this one that you draw, that's correct. That would be C3H8O, and that would be propanol. Got it? Yes, yeah. So switch to the 6 and draw the propanol and the propanone. How comfortable are you with the different functional groups?
I'm still trying to figure it out a little bit. I'm not too good in it.
Okay, but you know what the ketone functional groups look like? It's that C double bond O, right?
Oh, in the middle.
Yeah. So C double bond O, and then the aldehyde is CHO, right? So it's like C double bond O and then an H right there. I can show you the functional groups before we wrap up today. So let me see. So it's currently 5:53 right now, and we're planning on going until 6. How do you guys feel about that? Do you want to wrap up at 6 and then we pick up next time, or do you want to stay a little bit and just wrap up everything that we had today? I didn't have that much more, to be quite honest, but I want to know. I don't want to not be cognizant of the fact that we did say that we're gonna go from 5 to 6, right? So let me know, what do you guys think? Do you want to go a little bit beyond 5 to finish what we have for today? Or do you want us to pick up next week? It's not a lot that remains, but like, I just want to give you guys that leverage and that, so you can tell me what you want to do with your time, okay?
Let me see if we could go ahead with the extra few minutes.
Okay, what do you think, Kelsey and Beyonce? And I see that we have someone else that joined us, but I can't see the name right now. Let me look real quick. What do you guys think? Are you guys okay with that? So you probably would be, we can go ahead and continue. You probably would be maybe like 6:15 at the latest. I have a meeting to go to at 6, but I can stay until 6:10. Okay, yeah, we were not gonna go past that because it's what I said, no, 5:55. So once Sham finishes these 2 positional group isomers, we'll move on. And then he mentioned that he doesn't really have a good hang of the functional groups as yet. So I wanted to show you guys a table with the functional groups so you can see what they are, and so you have an idea of what they are in your head. So when you see them on a paper, you know immediately, oh, that's a ketone, that's an aldehyde, that's an alcohol, that's a carboxylic acid. What else do we have? That's an amine, that's an amide, that's an aldehyde, right? Those are the main ones that they want you to know for CXC. So I'm gonna show you guys what they look like before we wrap up here. So once Sham finishes this, then we proceed. We don't have that much left, but I wanted to just check with you guys that it was to continue with what we have for today. Okay, so Anish joined us. Hi, Anish, welcome. We're just like talking about isomers and structural isomers, particularly positional group isomers, and how we can have the position of the functional group in different places. And so even though you have the same molecular formula, when you actually draw the formula, right, like the structural formula, you see that it could be anything really. So if somebody gives you a molecular formula, without you knowing what they want, you could draw a variety of structures, right? So that's why it's good to know the different kinds of formulae and to be able to draw the structure yourself so that you can visually see what you're working with. Because as Sham drew, he drew here, you have both a ketone and an aldehyde. So the ketone is on the left. Can you name them for me, Sham? The ketone is on the left and the aldehyde is on the right. So can you name them for me? And then we'll just move on real quick.
Let me see, one on your right will be propanol.
Yeah.
And in the middle it will be this one.
And then the left one is propanone, right?
Propanone, yeah.
Okay. Why is my, let me just take that off. Okay, all right, so that's great, right? So that was very good, very well done, Sham. So let's move on to the next slide. So I'm just gonna clear the screen. Are we all clear on this? Anish, I know that you just joined in, but I don't want you to be lost. Is this clear to you? Anish, Kelsey, Beyonce, Shanae, is this clear to you? Okay, Anish says yes. All right, so, okay, so I'm just gonna clear your drawing now. Sham, I'm gonna clear it and then move on to the next thing, which is, let me clear this and move this back to here. Structural isomerism. All right, so we have now functional isomers. They have different physical properties and they have different chemical properties. So essentially what you drew is a functional isomer just now, right? They're gonna have different chemical. It's important to know what's gonna be different. So what you just drew, Sham, you drew an aldehyde and then you drew a ketone, right? Those are different functional groups, and the functional groups confer the chemical property of that compound. So the reactions that aldehydes participate in are very different from the reaction that ketones participate in. So if you have a different functional group, you're gonna have different chemical properties and also different physical properties, okay? So, I think we just did, this is a different one. So, but let's skip that for today. And then functional group, reactions and reaction mechanism. I'm just gonna jump and just show you a little bit about functional groups, and then we'll wrap up there, okay? So functional groups are atoms other than carbon or hydrogen, or groups of atoms that are attached to the main carbon chain, and these are called functional groups. So you have your main carbon chain, and then you have a group that might be sticking out here. Like in the case previously, we had that C double bond O, that's our ketone group. Then we have the C double bond OH, which is an aldehyde group. And so we mentioned earlier about these homologous series. So we have a series of compounds with the same functional groups. We call them a homologous series, and they're based on the alkene homologous series. So we will have, for the aldehyde, we would still have that first carbon being methanol, second being ethanol, and then the third being, what was the third one? The third one is propanol with 3 carbons, and then you have butanol. So you have a homologous series that's formed by you adding that extra carbon each time, right? And that's based on catenation that allows us to do that. And so here's an example. You have a hydrogen atom on alkanes that gets replaced by the hydroxyl group. So that's that OH group. And that enables us to form alcohols, right? And so on this slide, I'm just showing you like the vast array of functional groups that we have that exist in nature, or that we ourselves can synthesize based on our knowledge of organic chemistry, right? And I think if I remember correctly, I think that there are, so even though I'm showing you all of these, bring it back, where did it go? So even though I'm showing you all these functional groups, for the intents and purposes of CAPE, there are only a few of these that you have to know in and out. And of course, there are rules that you can use that I will teach you that you can use to know the specific chemical reactions that are unique to each functional group. So let me just tell you real quick the ones that you the student you're responsible for K, and then we can wrap up here for today. Okay, guys, so we're gonna just wrap up here now, but I'm gonna just show you the ones that are of interest and are worth your paying specific attention to as a CAPE chemistry student. All right, so alkanes, right? Check. Where's my pencil? Pencil. All right. So we need to know about alkanes. We need to know about alkenes, and that's this one with this double bond here. We need to know about halogenoalkanes or haloalkane. That's this one. And this is your halogen group. So this could be chlorine, bromine, any halogen, right? We are responsible for alcohols as well with this OH group. So that's your alcohol group. And we're naming them with all. So it's ethanol for the second one in the homologous series. We are responsible for aldehydes. And this here is our functional group. So that's COH. We name them ethanol. So there's that al right there. We are responsible for ketones as well for CAPE. So that's that CO group. And we have ON. So we'll have propanone, right? We are also responsible for carboxylic acids, which is COOH. That's that group right there, right? And we just say oic acid. That's what we name it. That's a naming convention. So we have ethanoic acid. We are also responsible for esters. So this ester is here. The functional group is this COOO, right? And you will say you name ethyl OH, so it's ethyl ethanoate, right? So we're responsible for esters. And we're also responsible for acyl chlorides. So it would be like this, right? This is an acyl chloride. It could be a chloride, but this would specifically for CAPE, we're focused on the Cl group. So if X is the Cl group, this would be our acyl chloride. So all of it then combined would be our acyl chloride functional group, okay? All right, so how many have we gone so far? We are responsible for amines as well. So responsible for this. So this functional group here is generally our NH2. Let me write that here since they didn't write it. But it's an R group. You have your R group, and then you have your NH2. That's an amine functional group, right? We're also responsible for amines, which you can see more nicely here, which is CONH2. So that's an amide group. We're responsible for that. And then finally, we are responsible for arenes, which are these ring structure. So it's this one. I skipped over it. It's this, right? So remember when I drew this, when I was talking about resonance, guys, remember this? Yeah, so this is your benzene ring, right? And so we would call that what? Ethyl benzene. So you have if you have this two carbon chain hanging off, we call it ethyl benzene. So how many is that, guys, that you're responsible for? You're responsible for all of those for CAPE. But don't worry about it. I will teach you some tips and tricks over the duration of this month so that you'll be able to navigate these different groups with ease, right? So what's that? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 that we're responsible for? Or is that 12? Why am I messing up right now? I think it's about 12, something like that. But we're responsible for all of these here for CAPE. So as time progresses, as we go along throughout this series of February, I will keep building on and adding on to this. But I hope I was able to help you in your fundamental knowledge and your fundamental understanding of organic chemistry today in some small way, you know, today. And then we will see you next time, which is next week, Sunday, at the same time from 5 to 6. But in the meantime, definitely feel free to engage with me, interact with me on social media. I'll have giveaways and questions throughout the week and study tips and motivational, like all kinds of stuff. So if you're not yet following me on that Instagram page, definitely do that. Feel free to do that. And then additionally, this will be on our YouTube channel afterwards. It's streaming live now. So you'll have it there and you can go and watch a replay if there's anything that went over your head today. And then definitely reach out to me if there's anything that needs to be clarified on your end so that we can do that before moving forward. We can do that before moving forward next week, right? Because as I said, we're gonna build. This is like building. We're building, right? We're building our knowledge in organic chemistry so that you will be able to answer any question that gets thrown at you because you have a firm foundation and you can identify patterns and trends. Okay, guys? So that's all I had for you today. Just some background stuff, and then we'll continue moving forward with everything. Okay, so let's see. Are there any questions for me right now? I can share the YouTube link with you so you can find the YouTube channel so you can see what we did today. I'm gonna share that to you right now. And of course, you have my email address, I think. So you have that, so feel free to email me. As I said, if you have any questions, anything you want to talk about, anything you want to work through on a deeper level, yeah, definitely let me know, okay? I'm here to help you as best as I can. So that's our YouTube channel where you can go and find this video being played back. If you're not yet following us on Instagram, as I mentioned earlier, I have a lot of nuggets, a lot of nice, cool things over there. And I'll have giveaways, so definitely follow us there. And then this is my email. So this is my email. So feel free to drop me an email if you want us to talk about anything that you're not understanding, and then we can move forward with that. Or if you want me to help you craft a study plan, definitely feel free to send me an email. So that's our email. Okay, guys? So if there are no questions, thank you for your time today. Thank you for attending. Thank you for being on time. But yeah, and I will see you next week, Sunday, at the exact same time. And tell a friend, bring a friend. My mission is to help as many students as I can from anywhere in the Caribbean. It doesn't matter. And so I'm happy that I have our Trini friends with us today. So thank you for coming. Tell everyone in your group that we're building. We did some basics today, some fundamental stuff. But as time progresses, we're going to keep building. So bring them in, and bring them as soon as possible so that they're not joining when we're done and we've already built the thing up already. Okay, guys? So yeah, you're most welcome, Beyonce.
Yeah, Miss, thanks for everything and much appreciated.
Yeah, thank you for coming and thank you for being such a willing participant. Okay, I really appreciate that. All right, so bye guys. Have a great week now, and I will see you on Sunday. But as I said, feel free to stay engaged with me and talk to me throughout the week on social media. I'll have questions for you to answer and win prizes and all these things, okay? So have a great week now, okay? Bye. You're most welcome, Anish.